You have seen that memory arrays are constructed by putting different bit cells in a 2D array arrangement. And the difference is in the way that we actually store each bit, specify what memory type we have. So we're going to go through some of the memory types. You probably have seen these memory types. So you have seen ROM and you have seen RAM. And ROM stands for read-only memory as opposed to RAM, which is random access memory. These names are historic and they don't represent the actual type of memory that we have nowadays. Okay, so for example, we still use ROM and RAM, and ROM stands for read-only memory, okay, but if you think about it, a read-only memory should be only read. Nowadays, this ROM actually can be erased and reprogrammed. This is what happens when you flash your BIOS, for example, in a computer. You're actually overwriting your ROM. So technically speaking, it's not read-only anymore, okay? It's actually rewritable. And also, we can think about random access memory, or RAM. Random access stands for the following. If you have a memory array, and that memory array has multiple rows in here, random access tells me you can access any row, for example, this one here, without first going through the previous rows. Which means that you can access any row within the particular memory array at the same exact speed. So reading row number 1 is not faster than reading the last row, which could be 1023, for example. It's not. Okay, they all can be read in the same speed because they can all be accessed randomly. And as it turns out, that ROM actually nowadays is also random access. So ROM is not only rewritable, it's also random access. And generally speaking, when we use ROM, we're referring to something we call a non-volatile or non-volatile memory, okay? What do I mean by non-volatile memory? Well, I mean that it is type of memory that if you switch off the power, so basically you take the battery off or the power is off, you're going to see that the type of memory or the data you actually stored in this type of memory is not going to go away. You turn on the power again, you're going to see it. This type of memory, you have seen it, for example, in flash memory, in thumb drives. Thumb drives are part of ROM. You basically put your USB, you program it, you take it, there's no battery in the USB stick. Okay, as opposed to RAM is called volatile memory. And what I mean by volatile memory is you will lose the data once you disconnect the power. So if you disconnect your computer from power and you connect it back again, generally speaking, the RAM we consider it unknown. You might have, it might stick for sometimes or whatnot, but generally speaking, you cannot trust what's on the RAM. You have to actually rewrite everything. Okay, so now what we're going to be doing is we're going to see how RAM and ROM are actually constructed and the different types of RAMs, which are DRAM and static DRAM, which stands for dynamic RAM, or static RAM, which is SRAM. So let's start with the dynamic RAM or a DRAM. And as it turns out that this particular type of RAM stores 1 or 0 by the existence of a charge across a capacitor or non-existence of a charge across a capacitor. So if a capacitor is charged and you put 1 on it, it's charged, basically considered the bit 1, and that's basically what the bit cell is. So the bit cell just have 1 in it because the capacitor is charged, as opposed to not charged, which actually have a 0. Okay, so what's the purpose of this transistor? Well, as it turns out that this transistor is just a switch. So this is an NMOS transistor. So whenever you actually activate the word line in here, you're going to see that you connect that particular switch. So that switch is connected. So you can see that the bit line is connected to the capacitor. If the capacitor is charged, you can see that this particular one will go to the bit line and I read it. However, if the capacitor is not charged, you're going to see that the bit line will have a 0. And this effectively how you read dynamic RAM. You'll be wondering, well, if the charge is in here and I actually connected it and I read it, the electronic, what happens is with this charge actually will disappear in here. So whenever you read it, whenever you read a 1, you're going to actually take that 1 will become a 0. So what happens with dynamic RAM is you're going to have some extra circuitry that restore that particular bit, because you might be just reading. You don't want to lose that particular bit. So there's something that we call a refresh circuitry, and it will actually refresh that capacitor. And the reason why we call it refresh is, as it turns out, the capacitor is not only if it's activated, you'll lose charge, it also loses charges due to leak, because we know electronic components are not ideal, so it's actually leaking. So every few milliseconds you're going to see that particular circuitry, which I'm not showing in here, it actually goes through all the capacitor and see if it's charged and make sure it's completely fully charged, or it might be just charging it again, and if it's discharged, it's actually just going to leave it that way. Problem with this particular DRAM, it makes it slower, because this particular refresh, you're going to have to always refresh it, and of course it creates some sort of a complexity with the circuitry that you're going to have to do with the refresh and how fast should you refresh it. Should it be millisecond, microsecond, nanoseconds, or whatnot? And the other thing is a capacitor. In order for you to transfer that charge from here to here, you're going to have to define or depend on its tau, which is the time constant of a capacitor. So generally speaking, you're going to see that DRAM is a slow type of memory. All right, so let's see a different type of RAM, and that basically is what we call a static RAM. In a static RAM, the bit is not stored as the charge across a capacitor or not. It's stored in what we call a cross-coupled inverters. So you have an inverter in here and an inverter in here, and they're cross-coupled. If something happens, you're going to see that the other gate is actually just going to refresh or restore the bit that should be stored. Okay, so a stored bit, and if a stored bit is in here, you're going to see whenever you actually activate these two NMOS in here by the word line, you have the bit line, and it's complement both at the same time. And you can actually check it at home and see that how it actually, if it's a 0 in here, you're going to put a 0 in here that made it the 1 in here, that made it a 1 in here, which made it the 0 in here, and so forth. It actually keeps that bit stored, and there's no need for refresh. This type of memory is faster because you don't need the refresh. These particular inverters probably would need 2 transistors to construct this, 2 transistors to construct this one. You need 1 transistor in here, 1 transistor in here. So the total we need is about 6 transistors. So if you take a look at the DRAM, the number of transistors we've used is just 1, and that's about it. So power-wise, you're going to see that the DRAM consumes less power because it only needs 1 transistor. You're only operating 1 transistor as opposed to 6 transistors in here. Area-wise on the chip, you're going to see that also the DRAM is smaller. A capacitor is extremely small to construct. 1 transistor will take a lot less space than 6 transistor. So DRAM, this is why DRAM is used, because it's less power and it's actually less area on the chip. So to recap, I'm just going to put all this information together and I'm going to put it right next to flip-flops. So you can see that in terms of speed, flip-flops are pretty much the fastest. They're extremely fast. The output is almost instantaneously available to you. And what you can see in here is it basically constructed with about 20 transistors. And because of it's about 20 transistors, that means it's big. It consumes a lot of power. So if you sacrifice a little bit of these transistors, you're going to see that the latency is medium here. And of course, the power consumption gets reduced, and the best power consumption will be in the DRAM. And however, it is slow. All of these are a type of volatile memory. Remember, this is RAM, so it's volatile. Once you turn off the power, all the transistors charge and whatnot, you're just going to lose all the data stored in it. And you can't just keep it between power cycles. All right, so DRAM, why do we still use DRAM? Of course, because it's low power and because it's a small area. You can see that across the years, because DRAM has these particular 2 powerful features, there were some other modifications to it to solve some of its throughput problems. So you can see that synchronous dynamic RAM was created, and it uses something we call a clock to pipeline a memory access. And more importantly, this is what you probably have in your computer. This is what you see. You probably have something called a DDR4, for example, nowadays. This is called double data dynamic RAM. What do I mean by double data? Well, all of these RAM are actually operational on the clock. As it turns out, this particular DRAM operates on the rising edge and the falling edge of the clock, so you have double the speed. And nowadays, this DDRAM operates at the speed of 1066 megahertz.